How's it going, Accelerated Chemistry? This is Mr. Spurk, and this is your Chapter 19, Section 3 notes on strengths of acids and bases. So we're going to first talk about strong and weak acids and bases. Acids and bases are classified as strong or weak based on the degree to which they ionize or dissociate in water. A strong acid is completely ionized in aqueous solution, such as hydrochloric acid and sulfuric acid. A weak acid ionizes only slightly in aqueous solution, such as acetic acid. Here's a good list of common acids and bases that we'll need to know. You're basically just going to want to know the strong acids, so hydrochloric, nitrous, and sulfuric acid, as well as your strong bases, calcium hydroxide, sodium hydroxide, and potassium hydroxide. If you know those six, then you know that everything else is a weak acid or a weak base. So if we look at these graphs, the dissociation of an acid, or HA, that H just representing the hydrogen ion, because we know that all acids start with H, in water yields H3O+, and an anion, A-. The bar graphs compare the extent of the dissociation of a strong acid and a weak acid. So in the top graph, we see that we have our acid, and we see complete dissociation. We see a bunch of hydronium ions as well as a bunch of anions. And then if we look at the weak acid, we see that we have our acid on the left, and it's going to dissociate a little bit. So we still have a lot of our acid, the green bar, and we have some hydronium ions and some acid anions. So we have an acid dissociation constant. Strong acids completely dissociate while weak acids do not. You can use a balanced equation to write the equilibrium constant expression, KEQ. So if we look at this equation, this is for acetic acid. So the KEQ we know is the concentration of the products over the concentration of the reactants. So the acid dissociation constant, or Ka, is the ratio of concentration of the dissociated form of an acid to the concentration of the undissociated form. So KEQ is equivalent to Ka. The acid dissociation constant, Ka, reflects the fraction of an acid that is ionized. Weak acids have small Ka values. Therefore, strong acids have large Ka values. Nitrous acid has a Ka of 4.4 times 10 to the negative 4, and acetic acid has a Ka of 1.8 times 10 to the negative 5. This means that nitrous acid is more ionized or more dissociated than acetic acid because it is a larger value. So therefore, nitrous acid is stronger than acetic acid. Again, here are just some more dissociation constants of weak acids. So some acids have more than one dissociation constant because they have more than one ionizable hydrogen, or they are polyprotic. Phosphoric acid, H3PO4, is triprotic. That should say triprotic because it has 3 hydrogens. It loses 2 hydrogens and it loses 1 at a time. Therefore, it has, say 3 dissociation constants. It has 3. So you see the first one is H3PO4 yields H plus and H2PO4 minus, and that has its own acid dissociation constant. And then that H2PO4 minus can lose another hydrogen, which gives us H plus and HPO4 2 minus. And then that HPO4 2 minus can lose that hydrogen to give us H plus and PO4 3 minus. And they each have their own acid dissociation constant. So we can calculate dissociation constants. To calculate the acid dissociation constant of a weak acid, you need to know the initial molar concentration of the acid and the H plus, or alternatively, the pH of the solution at equilibrium. Remember that KQ equals Ka, so we can set it up in a similar manner. Ka equals the H plus ion concentration times the anion concentration divided by the acid concentration. So let's try to give this a shot. In a 0.1000 molar concentration of acetic acid, H plus concentration equals 1.34 times 10 to the negative 3 molar. Calculate the Ka of this acid. So we're going to look at a new skill that we have not encountered yet, and it is called an ICE table. And ICE stands for initial, change, equilibrium. So what we're going to do first is we're going to write our chemical equation. So we have acetic acid, or ethanoic acid as they call it, but they are the same thing. So acetic acid is HC2H3O2. And when we put that in water, it dissociates into H plus and C2H3O2 minus. So down the left-hand side, we write ICE, I-C-E. Initial, change, and equilibrium. So initially, we have a solution of 0. Let's try this in a different color. Initially, we have a concentration of 0.1000 for acetic acid, and we have no H plus ions or acetic anion or acetate ions. What we do know is that equilibrium, the concentration of H plus, is 1.34 times 10 to the negative 3. So that is at equilibrium. So we write that on our equilibrium line. And since H plus and C2H3O2 are in a 1-to-1 ratio, we also have that much, or that concentration, of the acetate ion. So what this means is if we look at the hydrogen column, it went from 0 initially, and at equilibrium, it's 1.34 times 10 to the negative 3. So what this means is that the change was 1.34 times 10 to the negative 3. Same for the acetate ion. It increased by 1.34 times 10 to the negative 3. Now, since we have an initial concentration of the acetic acid as 0.100 and we had no hydrogen or acetate ion concentrations, this must have decreased by 1.34 times 10 to the negative 3. And when we subtract that, we know that our equilibrium concentration of acetic acid is 0.0987. So I know this is a little confusing, but again, this is something that we will talk about in class tomorrow. So let's draw our line and we're going to keep going. So now we have our equilibrium expression, or our equilibrium concentrations of each of our pieces of information. So that's what we're going to use here. So we know that Ka, or Keq, is equal to the concentration of products, so H plus, times C2H3O2 minus, over the concentration of the reactants, HC2H3O2. And now we have all of that information from our ICE table. So we just plug in all of these values. 1.34 times 10 to the negative 3 times 1.34 times 10 to the negative 3 all over the equilibrium concentration, 0.0987. And when we punch that into our calculator, we get a Ka value of 1.82 times 10 to the negative 5. And we know that from previous experience that our value of 1.82 times 10 to the negative 5 is a small Ka value. Therefore, this must be for a weak acid. And we know that ethanoic acid or acetic acid is a weak acid. So our math holds true. So we also have a base dissociation constant. A strong base dissociates completely into metal ions and hydroxide ions in aqueous solution. A weak base reacts with water to form the conjugate acid of the base and the hydroxide ions. For a weak base, the amount of dissociation is relatively small. Ammonia is a weak base, and it's used in many cleaning products. When equilibrium is established, only about 3%, it should be, of ammonia is present as NH4+. Let's fix that. 3% of ammonia is present as NH4+. The concentrations of NH4+ and OH- are low and equal. The base dissociation constant, or Kb, is the ratio of the concentrations of the conjugate acid times the concentration of hydroxide ion to the concentration of the base, which again is just the products over the reactants. Weak bases also have small Kb values, which means that strong bases have high Kb values. So we can also look at concentration versus strength. The words concentrated and dilute indicate how much of an acid or base is dissolved in solution. These terms refer to the number of moles of acid or base in a given volume. The words strong or weak refer to the extent of the ionization or the dissociation of an acid or a base. Even when a strong acid is diluted in water, it is still a strong acid. The same concept also applies to bases. So in review, acids and bases are classified as strong or weak bases, or weak based on the degree to which they ionize in water. And the Ka is equal to the H plus times the A minus over HA, and the same holds true for Kb. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook, the resources CD, and pearsonchem.com. Have a great rest of your day.